Rust is a systems-level language that is built to prevent crashes and eliminate data races. A language like C++ gives you high speed and lots of control, but it's easy to have segfaults, data races, and other problems if you aren't careful. On this spectrum of control versus safety, we can plot other languages like Java and Go and Haskell, but none of these languages have the unique feature set of Rust. Rust's concurrency model is built on the foundation of ownership. A piece of data can only be owned by a single thing at a time. In today's interview, Alex Crichton explains ownership and other abstractions that give Rust its unique model of concurrency. This is a good follow-up to the popular episode that I did with Steve Klabnik, who also talked about Rust. That was more of an introduction to Rust. So if you're interested in getting started with Rust, that's a good place to start. And then you could follow up with this episode about Rust concurrency. Indeed Prime flips the typical model of job search and makes it easy to apply to multiple jobs and get multiple offers. Indeed Prime simplifies your job search and helps you land that ideal software engineering position from companies like Facebook or Uber or Dropbox. Candidates get immediate exposure to top companies with just one simple application to Indeed Prime. And the companies on Prime's exclusive platform message the candidates with salary and equity up front. Indeed Prime is 100% free for candidates. There are no strings attached. Sign up now and help support Software Engineering Daily by going to Indeed.com/SEDaily. That's Indeed.com/SEDaily if you're looking for a job and want a simpler job search experience. You can also put money in your pocket by referring your friends and colleagues. Refer a software engineer into the platform and get $200 when they get contacted by a company, and $2,000 when they accept a job through Prime. You can learn more about this at Indeed.com/prime/referral. That's Indeed.com/prime/referral for the Indeed referral program. Thanks to Indeed for being a continued sponsor of Software Engineering Daily. If I ever leave the podcasting world and need to find a job once again, Indeed Prime will be my first stop. Alex Crichton is a staff research engineer with Mozilla. Alex, welcome to Software Engineering Daily.
Awesome. Thanks so much for having me here.
So we had a show about Rust several months ago, and it was quite popular. We interviewed Steve Klabnik, and we covered mostly the basics of Rust. And in this episode, I'd like to focus more on concurrency in Rust. So let's start with just the fundamental question of what is concurrency, agnostic of any particular language.
I'd see this kind of, there's a subtle distinction between this concept of concurrency and also parallelism, but I tend to view it just as two things happening roughly at the same time. As to whether they literally happen at the same time or they kind of interleave, but it's just kind of multiple things happening in parallel or concurrently, kind of all simultaneously.
Why is concurrency important today? Why is it always been important, and why is it getting more important?
The canonical way to explain that is that this whole Moore's law, where our CPUs get faster and faster and faster, is actually no longer true. Our CPUs are not getting faster, but what they are getting is we're getting more CPUs. So nowadays, your computer has 4, 8, or maybe even 16 cores if you're lucky. So somehow taking advantage of all this requires harnessing all this concurrency and kind of figuring out what to do with that to really use the hardware to its fullest value.
And why is that hard? What makes concurrency difficult?
Concurrency is not a beginner topic. It's taught very late in kind of any CS curriculum and is very difficult to reason about, and in general just has tons of nasty and weird and tough to uncover bugs. So it's generally been historically taboo to kind of work with, just because it's so difficult to wrangle, or it's so difficult to debug. Just kind of it ends up deterring so many otherwise prospective contributors for kind of working with all the extra cores.
So we could talk about concurrency on the level of a single machine with multiple processors having concurrent things going on. We could also talk about it at the level of different machines perhaps located at different places in the world because a distributed system operates in ways that are similar to a single computer in the scope of concurrency. How would you contrast concurrency in terms of how it manifests at different layers of the stack?
The hardware concurrency for multiple CPUs is kind of some of the more difficult to work around, where it has all these weird concurrency bugs or kind of segfaults that you've seen in the past. But once you go higher up the stack, it's a little easier to work with that kind of concurrency, where you would expect that these machines all over the place are kind of doing everything at the same time, and you typically have your points of synchronization, like your database or your whatever your what kind of browser client is or something like that. So I would probably characterize the higher level aspects of a distributed system as a little bit easier to work with, but still very, very difficult to actually get right in practice.
Okay, so let's start to talk about some of these particular issues of lower level concurrency that are difficult to reason about. What's a race condition?
So the technical definition for a race condition is when you have two threads doing, or at least one is a write to the same memory location, and one of the reads or writes is unsynchronized. And basically that's a fancy way of saying that you have two threads that are kind of working on one piece of memory, but they're not doing it with knowledge that the other one is doing it, and that ends up having a data race.
And if you have this kind of data race, what sort of user-level bugs could that concurrency issue propagate into?
Data race is undefined behavior, which means literally anything can happen. The canonical, I think it's demons fly out your nose, so all bets are off as soon as you have a data race in your program.
Okay. So before we jump into Rust concurrency and the protective measures that Rust gives you, we've had languages like C++ for a very long time. C++ is widely used for concurrent programming. What are the shortcomings of C++ as a language for doing this high-performance concurrent programming?
It's pretty similar to the basic general shortcomings of C and C++, where they're not really giving you a lot of safety or a lot of protection here. So they have basic primitives like atomics or mutexes or condition variables, but the way you use these is kind of you're on your own. You have to make sure that you yourself are principled in how you access data and how you synchronize data and how you work across these threads. So the language itself is not really giving you any tools or utilities to protect you, but rather it's just giving the fundamental tools for how to do this at all. So once you have that, it's very, very easy to make mistakes. Kind of when you work in this concurrent world, it's very easy to forget about a thread or kind of not consider this one case where everyone's in just the right order and causing a data race. So it's really the aspect of the language itself isn't really giving you a whole lot of help, but it's just giving you the tools to actually do it itself.
You describe C++ as making trade-offs between control and safety, and you talk about other languages in this spectrum as well. Why is there this trade-off between control and safety?
This has been a very classical viewpoint of, in the past, you either have control or you either have safety. And this basically, I mean, at least from what I've seen, comes out from garbage collectors, where everyone assumes that C and C++ give you all the control and no safety. But on the other hand, once you start adding a garbage collector, you start losing all this control, but you have a whole lot more safety. But Rust is kind of taking this and stepping off of that, saying there actually isn't really it's not a fundamental trade-off between control and safety. It's kind of in our historical precedent and kind of historical in our minds.
Can you talk more about that and explain why there's that connection between garbage collection and this control and safety trade-off that may or may not be a truthful representation?
Well, so a garbage collector kind of the first thing it does is it takes away a lot of control from you. So it's this big, massive runtime running in the background, which can non-deterministically pause your entire program just to go collect some data or trash some various values. So this loss of control means that when you're writing a program, you no longer have this very clear and crisp understanding of what instructions are actually running on your machine. It'll be taken over at any one point from you. But on the other hand, it's giving you this very large level of safety where you no longer have to worry about use after freeze. You no longer have to worry about, almost like a data races, because a garbage collector tends to take care of that. But just these general memory management issues are all handled by the garbage collector. You just throw all the memory at it, and it'll take care of it, and it'll kind of do whatever it wants with that. Whereas C++, on their hand, is giving you this very clear control of what's happening, but then you can very easily shoot yourself in the foot. You can have double freeze, you can have data races, you can have memory corruption, all that fun stuff.
There are many languages that you also describe on this spectrum of safety versus control, like Go and Java and Scala and Haskell. How do these languages fit on the spectrum? Is it all a measure of how they do garbage collection?
It's kind of, at least the way I think of it, is not only the garbage collector itself, but also a level of kind of the type system behind it. So I would put languages like Go and Java kind of roughly in the middle of this kind of control and safety spectrum, where they're giving you a whole lot more safety than C and C++, but not entirely. Like there's still some ways to get around types at runtime. There's kind of various things you can do there. But then if you actually go farther towards the safety aspect, less control, you get to like Scala or Haskell. Haskell's kind of the best example of this, where you have very, very powerful guarantees about the safety of your program, but you have almost no guarantees about the runtime because it's all lazy and you don't actually know, kind of like even the big O for simple algorithms, it's very difficult to reason about.
Now let's start to get into Rust. Rust is described as a systems-level language that is built to prevent crashes and eliminate data races. How does Rust do that?
So the number one feature of Rust is the ownership and borrowing system. So it's this kind of simple concept in the sense of data has an owner, and then you can kind of borrow that at any one point in time as long as you hand it back at one point. And these sound like relatively simple concepts, but this ends up having a very massive impact on all of Rust as a whole, and is kind of where the linchpin of our concurrency story, of our memory management story, of our memory safety story, all comes down to these ideas of ownership and borrowing.
So let's get into those in more depth. Let's talk about ownership first. A piece of data can only be owned by a single thing at a time. That's the concept of ownership. Why is it so important?
This basically gives you a very clear understanding over, if you know who owns a resource, you now know precisely when that resource can go out of scope, or when it does go out of scope, and also what to do when it goes out of scope. So you can deallocate it, you can do whatever you want with it. And then having this clear owner also means that they're allowed to do whatever they would like to that data. So they can mutate it, or they can read it, or they can pass it to someone else. And at the same time, if they are the sole owner of this piece of data, then you can be very confident that no one else is looking at it, even in a concurrent setting, or just there's no extra references. So if I deallocate this, it's impossible for anyone else to read this because they don't have reference to it, as I was the owner of that data.
Do other languages have this model of ownership in some form or fashion?
As far as I know, I think this was pioneered in this language called Cyclone, which I know very little about, other than that it has a concept of ownership. But beyond that, this kind of static checking of ownership that Rust has, I am not aware of, at least in any. It's certainly not in any of the mainstream languages, as far as I know.
Okay, so with ownership comes the concept of borrowing. How does borrowing work?
So it turns out if you only have ownership, it's a pretty crappy system because you have to like pass around all these values by value, kind of like whenever you pass a parameter or function, it has to give it back to you if you want it back. So the whole concept of borrowing is that I don't always want to give you ownership. Maybe I want to kind of let you read this or let you write to this for a very short period of time. So I'm going to give you a borrow of my piece of data, but you're going to return it before I keep running again. So the idea with this is that I'm not giving you ownership, but I'm giving you either read-only or read-write access to a piece of data. And then the compiler can also statically ensure that before my ownership ends, then your borrow has also ended. So it's kind of this intermixture of allowing people to touch the data, but not allowing them to touch the data beyond the lifetime of the actual object itself.
You describe this model of safety versus control being somewhat, or Rust is somewhat agnostic of this safety versus control trade-off scheme that we mentioned earlier with some other languages. Why is Rust able to be absolved of that, through its concepts of ownership and borrowing?
With ownership and borrowing, we can kind of give you a safe language by default. So when you use Rust, you actually never have to worry about segfaults or data races or corruption or any of those old classical problems in C and C++. But conversely, Rust still gives you so that all comes with a level of there's no runtime behind this. This is all a static check. There's nothing happening behind the scenes when you're actually running your program. So that allows you to have, even with ownership and borrowing are happening, you have very high control over what's actually happening underlying on the system itself. And then furthermore, Rust also has this escape hatch for unsafe code, saying that in this little block of code, I'm allowed to do some kind of weird things I wasn't allowed to do before, which might break some invariants, but I'll kind of make sure I contain it to just that unsafe block. So this is kind of the extra, the final mile, that last 20% of not everything can be expressed with ownership and borrowing, but you can kind of put a guise around that with little unsafe internals, which allows you to basically get the full level of control over the machine by allowing you to do essentially anything, but all the while maintaining this safety guarantee at the very top layer.
Okay, so that word safety, let's talk about that in more detail. The core concurrency primitives of Rust are built to be 100% safe. What does that concept of safety mean?
So for us, we define that in the concurrent setting as no data races. So this means that no matter what you do, you cannot get a data race in safe Rust. And then it also comes the whole general, like, no easy up to freeze, no memory corruption, no double freeze, no anything like that.
Continuous integration gives you faster, safer software delivery. With a continuous integration tool like Snap CI from ThoughtWorks, the members of your team can push changes independently of each other, and they can all see their new builds running against different phases of tests before those changes make their way into production. The fastest moving companies that I've talked to on Software Engineering Daily are all using continuous integration. Snap CI from ThoughtWorks is available to anyone. And if you go to snap.ci/software engineering daily, you can check it out for yourself and support Software Engineering Daily. With just a few clicks, I had my own continuous integration set up for some projects that were just sitting in my GitHub account without continuous integration. I got continuous integration up quite easily using Snap CI. If you want to be that hero at your company that starts moving your organization towards deploying often, more confidently, towards that DevOps dream, start working with Snap CI at snap.ci/software engineering daily. Your coworkers will see you working with Snap CI, and they will fall in love with it themselves. Oftentimes, it takes somebody at a bigger company to go out on their own and say, okay, I'm going to roll out CI even though nobody else at the company is using it. And maybe that hero at the company is going to be you. So check out snap.ci/software engineering daily. And thanks to ThoughtWorks for being a continued sponsor of Software Engineering Daily. It really means a lot. I mean, my understanding is avoiding those kind of issues in C++ has a lot to do with some locking and synchronization type of stuff. Can you explain, I don't know, how other languages do that in more detail, and maybe contrast that with Rust? Like, does Rust have a way of avoiding this type of locking behavior by the virtues of its borrowing and ownership?
So it's actually what kind of Rust will compile down to, kind of when you write your program and it compiles and it runs, is very similar to what you would do in other languages. So the primitives that you get in Rust are no different than the primitives you get in C and C++ or in Java or Go or anything like that. We have blocks, we have condition variables, we have message queues. The difference is that, for example, in C and C++, you can use a mutex, but you don't have to use a mutex. You can actually still access the data outside the mutex, outside the lock. You could share a piece of data that you still have access to. You can kind of, even when you're using the standard synchronization primitives, kind of the accepted solution that everyone wants to use, you still have all these pitfalls that you have to watch out for. So conversely, on the Rust side of things, no matter what you do, no matter how you use these primitives, you cannot misuse them. So kind of the best practices and the only practices, kind of the only safe practices, are codified in APIs here in Rust. And then with this ownership and borrowing system, that's kind of the static guarantee we overlay on top, saying it is impossible to misuse these. You just don't have to worry about those problems, the same kinds of things you have in C and C++.
It sounds like C and C++ are loosely safe, and Rust is strongly safe, perhaps.
In a sense, yeah.
Okay. So let's talk some more about these abstractions that Rust provides you. It's not just limited to ownership and borrowing. Rust has the abstraction of a channel, which allows processes to communicate. Can you give an example of when a channel is useful?
This is kind of, you might have some worker task, which is producing some data over time, and you just want to periodically send the results to some other consumer task. And that's kind of one of the better examples of a channel. So let's see. I could be having a list of files in some directory. Maybe I'm calculating some checksum of them. So I'll periodically, I want that to happen concurrently. So I'll kind of periodically send you the checksums that I'm actually calculating. But in the meantime, you can go and do whatever else. And then later on, check out and see, oh, what are all the checksums I just calculated?
And how does the safety of a channel get enforced in Rust?
This is kind of, when you create a channel in Rust, you'll actually, instead of getting one value, you get two things. You get the sender half and the receiver half. So this is kind of the first thing you'll see in Rust is kind of splitting up the ownership of those two pieces. And this is because all of our channels are multi-producer, single consumer, which means they're only safe if one person is receiving messages and possibly many people are sending messages. So we can codify that by saying the receiver, this owned value, is the only one that can receive messages, whereas the sender, you can create a bunch of copies of it and send it to a couple places. So that's the first thing, is you have these split halves of the sending half and the receiving half. And then once you add on top of that, the type system itself ensures that kind of if this channel crosses a thread boundary, so if I'm actually literally doing this concurrently, the type of data that's being sent across this channel has to also be sendable across this channel. So we have this kind of static guarantee that I'm not accidentally sharing a ref counted piece of data that's not protected. It's not a thread safe ref count. I'm not accidentally sharing data across these two threads that's not safe to be shared across these two threads. And then you also get the same static guarantees you have in other pieces of Rust with type parameters of that I'm not sharing data that's kind of alive for too short a period of time. So I know that if I send you a piece of data, it's going to be valid when you receive it, and you don't have to worry about it going out of scope or being destroyed behind your back.
If I have a large data set that I want to share between processes, there's something called an arc pointer that I can use. How do arc pointers allow data to be shared safely?
Yeah, so this is where message passing doesn't always cover all concurrent use cases. So we have a suite of options, one of which is arc. And arc stands for atomically reference counted. And what that means is that this piece of data is put on the heap with a number next to it, where the number says how many people are accessing it, or kind of how many people have a reference to it. And that number is updated and decremented atomically, so it's kind of managed in a thread-safe fashion. And then we can ensure that because of that, you can have many references, and you're not really sure when you'll actually destroy it. It's kind of a form of garbage collection in that sense. But you know that once all the references go away, we can safely deallocate all the data. And then at the same time here, while we're also managing the reference count for kind of when we destroy this data, Arc also imposes the restriction that the data itself can be accessed by multiple threads at one point in time. So it's kind of the point of Arc is that you have this shared ownership across many threads, but what that implies that the data itself has to be prepared for concurrent access. So Arc kind of gives you that static bound and kind of ensures that that's happening.
So an arc pointer is a case where we want to share memory. Channels are a case where we would want to share some memory. What are some other circumstances where we would want to be doing sharing?
I think another big one would be with mutexes, where I was saying that with Arc, you have this sharing, but you have to be prepared for concurrent access, which not everyone always is. So like a vector or a hash map aren't always concurrent. So a mutex is typically something you put inside of an arc, saying a mutex is safe to concurrently access, but the data inside the mutex you don't have to worry about at all. You can just you can mutate that, you can access that or read that. It's all done in a synchronized fashion where mutexes block owners of that mutex itself.
Are there any other core concurrency primitives of Rust?
Pretty much the standards. So we have condition variables, which are useful for sending notifications or kind of what a lot of message queues are built on from time to time. We have RW locks for both reading and writing, so you can have many concurrent readers, but only one writer at any one point in time. And then the last one that I can think of is, like in Java, we have methods for parking and unparking a thread. So this is kind of the crux of many concurrent algorithms you'll see in Java that have to do with things like that, where the idea is it's a very lightweight way to block a thread or unblock a thread. And this is typically used as a building block for even further concurrency algorithms, kind of building up more and more abstractions outside the standard library itself.
Okay. So in order to kind of catch up the listeners if they've maybe lost track a little bit, and now that we've discussed some of the concurrency primitives, can you explain again how Rust avoids data races?
I was saying earlier that the strict definition of the data race is two concurrent threads, one of which is a write, and one of which is unsynchronized to kind of one memory location. So the core of Rust with ownership and borrowing is preventing this actually from happening. So the first thing we have is two threads. So already that's actually very difficult with ownership, because typically whenever you have a piece of data, it's very difficult to have more than one person accessing it at any one point in time. So ownership is already this kind of hard guarantee that you can't have, it's very difficult to have two people sharing a piece of data. So the next thing was at least one of them is a write. So you can actually only write through what we have as a mutable borrow. This is where in Rust, this borrowing system gives you two kinds of borrows, the shared borrow and the mutable borrow. So once you have a mutable borrow, no one else can have a mutable borrow, so you're guaranteed there can never be two threads. So you're already ruling out that system as well. And then finally, once you have a shared borrow, that's the only case you can have where two threads are writing to it. But that's where we're in such a controlled environment at that point that we can always statically ensure that if you happen to have a write right there, one of them is synchronized, or like they're both synchronized, and we can handle that.
So in order to perform concurrent modifications on data in Rust, particularly if it's like a sophisticated situation that's going on, complex program, the user can compose together these different concurrency primitives. So give an example of how that's possible, why that would be useful.
Let's say you have a system which is primarily message-based. So you're sending a lot of data across channels. You're kind of like having workers and queues processing throughout the system. At the same time, you might also want a very large chunk of data, kind of like some global state or a global context, to be shared amongst all these workers. So that's where you might put in an arc. So primarily you have all these channels pushing through, but you also have this arc protecting some global data. And then maybe at the same time, you could have a global counter, or maybe like an extra suite of global state, which even needs to be mutable. So inside that arc, you might also have a mutex to kind of put that together. And then all along the way, the channels might not always be these concurrent channels in the standard library, but they could be kind of channels built externally in the ecosystem. And that's where you might be using this thread park and unpark, or maybe condition variables or Deadlocks. So you can kind of see, depending on what the system is doing, you have a nice mixture of basically all the concurrency primitives that work there.
Mm-hmm. So the holy grail of any concurrent language is a lack of segfaults. Could you explain how a segfault typically occurs in a language like C++ and how that is avoided in Rust? I realize this is, again, just like digging into C++ versus Rust, but I think this kind of gets at the core appeal of Rust as a concurrent language.
Especially in a concurrent setting, at least from what I've seen, segfaults typically come because of a use after free or a memory corruption. So a use after free typically means that there was some resource which was deallocated, but it was deallocated while there were still active references to that. And it was kind of this knowledge, it was forgotten or mistaken. So then these stale references, then you go access it later. And so that in a concurrent setting means that one thread would deallocate something while some other thread is reading it. And so that's where one possible segfault could happen. And so Rust prevents that by, in the sense, like with ownership and borrowing, we know that once a piece of memory is deallocated, there are zero references to it, so we no longer have to worry about that. And then the idea of memory corruption is kind of the other one for segfaults, where I can pave over some invalid data, but I wasn't expecting someone else to do that, and then as I read it, I kind of follow some dangling pointers. So in this case, that's basically the concept of a data race, where I wasn't expecting someone to kind of pave over a bunch of data here, but then they actually did. And that's where Rust's guarantee that you have no data races in your program can prevent those segfaults.
Another set of concurrency problems that are canonical are deadlocks and starvation. Do these show up in Rust?
Yes, they do actually. This was in very early versions of the standard library. We attempted to statically prevent deadlock or kind of help out with the starvation problem. But unfortunately, the models which we had there were so restrictive that they kind of ruled out so many valid programs, it ended up not being worth it. So today, although Rust prevents data races, it does not protect you from race conditions, which are subtly different. One causes segfaults and one doesn't cause segfaults. So these conditions of deadlock or starvation are still very much possible in Rust. You just have to, you would have to be vigilant to still rule those out.
So why was it so restrictive? Were there just too many programs that look in some form or fashion like they're going to be leading to deadlock or starvation, but it's actually something that's desirable?
Yeah, that was basically exactly what happened. The way it was encoded was that if you kind of had mutability inside of mutability, it's kind of, I forget the exact specifics, but it was basically totally benign programs were like, this could deadlock. You read it and you're like, no, there's no way that could possibly deadlock. So it had so many false positives and is generally a very difficult problem to solve. We ended up punting on that for the standard library.
Mm. You gave a talk recently about futures in Rust, and I think this is another angle on concurrency. How do you define a future?
Oh, I love this question. So I define a future as a sentinel for a value which will become available at some later point in time. And that's basically a fancy way of saying is that a future is an object which is a proxy to something which is being computed elsewhere, like something in another thread or some HTTP request coming in, but I can talk about it through this actual concrete object.
Now, I think of futures as increasing in importance because we have all these circumstances where, for example, a page loads and in order to load that page, you have to request resources from a bazillion different sites. You've got these, you're loading these images over here, you're loading this, text from an external API over here.
Right.
And in all of these circumstances, you've got non-deterministic time, because you have to go across the network to request, and you don't know how long that's going to take. It's going to take a variable amount for the image versus that external API or whatever it is. So would you agree with that? Is that at the core of why futures are increasing in importance?
I think that's a very large portion of it is kind of making sense of all of these concurrent systems and kind of all these requests flying around. But I think it's also the other half of it is just expressing that at all. So you can imagine that, let's say you have a system that's kind of doing all these crazy fetches. It is a web browser. Then making sense of that and writing that and actually debugging that and working with that and developing it over time can be very difficult depending on how you're actually expressing it. So futures is kind of giving you this order to the madness of making sense of all of that, making it easy to write, making it easy to understand, and kind of you can work with it and debug it and develop it over time much, much more easily than you could with kind of just doing everything in a raw fashion.
So you've got a bacon delivery service, and you need to notify your customers when their bacon has arrived at their doorstep. Twilio helps you make sure your customers get the bacon while it's hot. Twilio's programmable API lets you build SMS or voice alerts easily in the programming language of your choice, all in under 5 minutes with only a few lines of code. Now your customers get a text or a call the instant their bacon is ready. If your customers want to see the bacon frying on a hot pan, Twilio has video APIs and SDKs for the platforms that you know and love. Learn more at go.twilio.com/podcast and get an additional $10 when you sign up and upgrade your account. That's go.twilio.com/podcast. You will only pay for what you use, and it costs less than a penny to send a text. Get started at go.twilio.com/podcast. Get your bacon delivery service cooking with Twilio's APIs for voice, SMS, and video. Like the other concurrency primitives that we've discussed, you can use futures to compose together sophisticated logic. Explain why that is. How are people typically composing futures together?
Yeah, the my favorite commonators here kind of are like the way to compose features is with the idea of a join and a select. So on features, just kind of every single feature in Rust, you can join on it saying, I want to wait for these two features to complete. I want to wait for both values to become ready, like whatever they are. They could be a database request, they could be an HTTP request, they could be a channel send. Or you could say, I want to select. I want to wait for one of two features to complete. So you can wait for the first of a database request or an HTTP request, or the first of a message send or a database request. So kind of these very simple concepts of waiting for two things or waiting for one thing, doing that in a generic fashion across all features ends up being very, very powerful and is very expressive in terms of working with these very highly asynchronous systems.
Mm. So sometimes a feature only represents a single value, but there are other circumstances where you might want to use a feature as a stream of values. When would this be useful?
So the standard libraries channels are actually a great example of this, where the receiver end of these channels that are just getting all these messages is actually a stream of messages over time. So there's no kind of one feature that represents that thing itself. But once you have a stream, you can it is itself a feature, but you might want some specialized constructors or some specialized combinators to transform that stream, such as if you want on a feature, you can transform the type. So you can take a feature of a string to a feature of an integer by parsing it. But for a map, or you can also do the same thing for a stream of values. You just have this operation that runs many, many times as opposed to only one time. So having these two distinct concepts allows you to kind of work with each of them independently. And the other one that I should also mention is that one of the most perfect examples of a stream is a TCP socket. So if you're listening for TCP connections coming in, that itself is a stream of TCP connections being pulled off and like going and dealing with those. So that's kind of like at the fundamental base layer of any server is a stream you can start building up on top of that.
So you worked on the future support for Rust, is that correct?
Correct, yeah.
What were some of the subjective design decisions that you made when working on Rust futures?
Well, no, it's interesting because we started out with many sort of subjective subjective designs. So we had we used callbacks, and then we had requirements of send and static, which means that data can be sent across threads. But over time, we actually ended up realizing that all of these subjective decisions or all of these kind of subjective concepts were too limiting. So they just imposed too much runtime overhead, or they didn't cover all the use cases we wanted to cover. So in the end, what we actually ended up doing was almost removing everything subjective about the library. So the only thing left is kind of, I would say the most subjective part is we have this idea of a task, which is that every feature has one task that's kind of driving it to completion. You can kind of think of a feature as like a function and a task is like a thread in kind of blocking Rust. So this concept of a task, you can block it occasionally. You can then wake it up once it's actually blocked. That's probably like the most subjective part of features. But other than that, we've tried our best at least to strip out basically everything else, giving you the core bare bones of features that's as flexible and kind of extensible to as many situations as possible.
There is a stack called Tokio in Rust that helps with asynchronous I/O. Can you explain what Tokio is and why that's connected to what we're talking about right now?
I would love to. So Tokio is aimed at being a one-stop shop for async programming in Rust. So the idea here is that it is built itself entirely on features and streams. So that's just the core fundamental layer of this entire stack. And then as you go up the stack, kind of as you go up this library, you get more and more functionality. So we have an event loop based on features and streams. We then give you TCP and UDP on top of that. We have protocol parsers built on top of that. And then finally, we can get up to this layer of servers and services. So if you're familiar with Finagle, Tokio is very much inspired by that and is very much doing basically accomplishing a similar task where it's a very simple way to define and compose various servers together, servers and services. So Tokio is kind of giving you all the pieces of the toolkit for managing an asynchronous I/O system, for managing tons of servers, high-performance servers, all these async things flying around. And Tokio is kind of the one place to go to actually get started and work with all of that.
Finagle, I think we did a show on this a while ago. I think it's like Twitter's project, and like they originally came out of Twitter. And something that the tagline for it is like some kind of network proxy or something. Maybe you could explain that in more detail.
Oh, I didn't know. I didn't know about the tagline like that. But as far as I know,
I don't remember. Maybe I don't remember the tagline. I'm probably misquoting it.
As far as I know, Finagle is a framework written by Twitter in Scala to kind of manage all of their microservices and kind of compose all their frameworks. And it's mostly centered around this concept that there are separable pieces of a server like failover or load balancing or kind of like network monitoring or tracing or hooks around all that are actually separable. And basically it means you can write them once and everyone can use them afterwards. So one person wrote the failover module and now everyone's using failover, or like everyone can use failover as a result of that.
Interesting. So why is that? Why would you build that why would you build that for Rust exactly? Or can you explain that in more detail?
Yeah, certainly. We see
I guess it's
Rust.
just for any server application that you would want to write in Rust, it would be useful to have these types of server support functionality in the same language.
Exactly. This is where right now Rust on the server is kind of a fledgling ecosystem where it's not quite kind of realized to its full potential. So this is part of our push to kind of make sure that Rust is perfectly ready to operate on the server in the sense of many other languages as well, and giving you the full suite of tools you would expect kind of all in one little toolbox organized.
So once you have this kind of library that helps with asynchronous I/O and helps with all this support for having Rust on the server, you get these things like tracing and whatnot. What do you actually build on top of that, or what leverage does that give the average developer?
The biggest selling point of Rust, in my opinion, for Rust on the server is that this gives you the ability to write incredibly high-performance servers that are also as understandable or as maintainable as kind of the servers you would expect today. So the idea is that if you're working in Rust, or if you have any need at all for something to be very high performance, but also maintainable over time, the maintainable over time kind of kills the C and C++ aspect, but the high performance aspect, at least in my personal opinion, the high performance aspect you can get from Rust. So the idea is that this not really, I mean, it's somewhat of a niche, but it's also a lot of people need it. It's kind of serving that need of here's how to have a system that is maintainable and scalable, while at the same time it's a lot of fun to write with in Rust as well.
It's interesting what you say about the C++, like kind of just breaking the maintainability, because I remember, I think I've worked at a couple places where there is one person who is in charge of the entire C++ code base, and he was the only person in both cases who could support this C++ soup of code, and nobody else could wrap their mind around it. It's just like too hard.
I mean, you'd be surprised. That is essentially almost always the case. Unless your name is Google or Facebook, then you're probably in the same situation. We've had a number of companies talk to us basically with the exact same story, saying we had one person on the C++ code base, they left, and now everyone is terrified to modify it. And that's the exact reason for choosing Rust, where with Rust, you don't have to be terrified. It's kind of this is kind of this concept of hack without fear, where anyone can kind of jump into code base, anyone can kind of play around with this, and you don't have to worry about breaking the whole system or causing segfaults or doing all this crazy stuff.
So you work at Mozilla.
That's correct.
Why does Mozilla need Rust? What kinds of applications, particularly with regard to control and safety and these concurrency issues we've been discussing?
Yeah, totally. So in my mind, kind of one of the best showcases for who needs all this control and safety is a web browser, where a web browser needs tons of control over the actual system. You're writing JIT compilers in it. You're doing crazy rendering. You're having this insane networking stack. So the browser and like the bread and butter of browsers is this performance war. Everyone is trying to be the most performant web browser, beating out the whole competition. So that's where control is definitely necessary when you're writing this. But at the same time, a web browser is your gateway to the internet. And we all know that the internet's not exactly always the safest place, so we really need a web browser to be safe at the same time. Now, all current web browsers are written in C++, and unfortunately, it's not giving us the safety aspect, so we see a very routine set of vulnerabilities in web browsers, kind of escaping the sandboxes or taking control over your system. So Rust was kind of this initial idea at Mozilla a couple of years ago. I don't even know how many. It was at least 5, if not 6, where the idea of what if we started from scratch? Well, this is a very long-term bet. Let's just start with an entirely separate tool, a language that is safe and gives you all this control by default that's very difficult to break out of. And then at the same time, let's kind of prove this out with a web browser itself. So Mozilla's been in development with Rust in tandem is this browser called Servo, which is a research project from Mozilla, which is a web browser written in Rust, kind of exploiting all of the safety and concurrency guarantees you get in Rust to do all this really cool things in the web as well, to see how we can actually accelerate the web just by building a new web browser in a language like Rust. So that's kind of the motivation for why Mozilla originally got in this game. And then it's ended up paying off quite well, where we'll start seeing a lot of Rust in Firefox itself. And so that's Mozilla's continuing and ongoing investment in Rust.
What is new about that browser, Servo? Like, why is Rust important to it, or what kinds of features are you able to build into Servo that would have been harder without Rust?
So if you take any existing browser engine, you'll notice that it's not exactly exploiting all of your cores to the fullest extent. So this whole Moore's law or concurrencies, browsers aren't actually taking advantage of all that. They are in some cases, but certainly not in all. But the problem with this is that if you ever tried to retrofit parallelism onto a million-line C++ code base, you'll find it's actually quite difficult. So it's very difficult for modern browsers to take advantage of all this hardware, and it's just kind of lying there waiting for someone to make use of it. So the concept of Servo is to actually make use of all the cores you have on your system. And it shows itself primarily through parallel layout. So the idea of, given a web page, kind of all these HTML documents and whatnot, how do you actually translate that to a bunch of boxes on the screen itself? And so what Servo has been doing is doing all of that in a massively parallel fashion with work stealing and all the fun algorithms like that, and is showing some insane speedups compared to modern browsers and like rendering of a page, layout of a page, kind of isolating these various tasks, but having the Rust safety guarantees at the same time mean that this is scalable over time, where no one has to worry about breaking the whole system as long as they're staying in the safe subset. They can be assured that even though they're changing it, they're not, and everything is crazy happening concurrently, they're never going to segfault. Everything's going to be nice and controlled at the very end.
Are there any problems that introduces, any complexities or unanticipated difficulties?
It's true because so CSS itself, kind of where all the layout is coming from, was not engineered to be amenable to parallel layout. So it's been a pretty insane undertaking on the Servo team to kind of exploit parallelism as much as possible. And they've done really, really well with that. But I think also it does have a bit of a tax on the system in terms of some workloads might kind of hammer the DOM in a particular fashion, which for normal web browsers is fine because they have synchronous access or kind of not everything is parallelized. But in Servo's use case, if it happens to be parallelized in just the right fashion, then the cost of doing these various accesses might impose some synchronization overhead. So kind of flushing those out over time, discovering what's happening, and kind of figuring out how to paste over that as well has been difficult to work with. But also, I mean, these are all kind of micro benchmarks as opposed to like actual everyday browsing experience.
What is it about CSS that has to be so, I guess, serial?
I think it's one of those. So I would say I have yet to actually contribute a patch to Servo myself, so this is mostly hearsay.
Okay.
But it's something along the lines of just the way the spec is laid out, the way the spec describes all these operations is kind of relative to this previous box, and kind of this is how the margin goes in, this is how the position happens. So a lot of it is very tree-based, where you have to compute your, like, everyone to the top and the left of you to actually figure out where you are afterwards. So that kind of, it's in that sense, it's a very sequential process, but which has like opportunistic parallelism inside of it. So some pages have no parallelism almost at all. Like their entire layout is only amenable to kind of one box at a time, and that's it. But other pages are much more amenable to parallelism, where you can kind of say, okay, this region inside of it, I can do all of that in parallel compared to this region over here. So it does kind of depend on the web page itself, where the exact structure can mean that you lay out more in parallel versus more sequentially at any one point in time.
Did you see the Dropbox transition off of the cloud and their emphasis on Rust in their new application platform?
I did indeed. We've been closely talking with them about that, both before and after that.
So why does Dropbox use Rust so intensely? Like, I guess, I don't know, when you talk about Tokyo and you talk about building in the support for this asynchronous I/O that where it just works out of the box if you have a service and all your services are using Tokio and using Rust. That sounds like something that would be quite appealing to Dropbox.
Yeah. The specific case that Dropbox has is, so they've primarily written a lot of their software in Python and Go historically. So they were in moving the storage system from the cloud to kind of S3 to their own in-house system. They have these certain components of that which deal with a lot of data and have very strict latency requirements. So this is where the actual things running on the machines that are kind of putting all the blocks in various places, managing the storage. This service was written in Go at one point, but they noticed that the GC pauses, the jitter, the latencies were not quite what they wanted. It just wasn't working in a small enough footprint. So kind of managing all this data required so much memory, and it was so variable over time, it was difficult to reason about the machine. So this is kind of where they first started looking at Rust, where their constraints were they wanted a very predictable memory usage. They kind of wanted a nice flat line to see what is the proportion of data managing to memory required to manage that. And they also wanted a very fast turnaround time on this. They wanted very predictable response times to say, I'm returning very quickly here. And then at the same time, this is protecting your data. This is actually managing your data on the lowest level. So they want it to be incredibly robust and incredibly reliable, because this is if you lose data at that level, it's almost catastrophic. So this is a perfect use case for Rust in terms of giving you all the performance requirements you need from a language like C++, but also giving you the reliability and robustness guarantees that you would like to expect from Go as well.
Mm. I thought this transition was one of the most impressive things that I've seen in doing coverage of on Software Engineering Daily. And I don't know. I always like to comment on this whenever I get the chance, because there was some period of time where I was like, "What is Dropbox doing?" Because there was like the common criticism was like, "Oh, there's no new features coming out of Dropbox. Nobody cares about Dropbox anymore." And then they come out with this Wired article. It's like, oh yeah, we've been spending the last 2.5 years moving off of AWS and building our own cloud. And it's just like, oh my goodness, that's pretty good. That's pretty impressive.
I was actually working at Dropbox before I worked at Mozilla, and this is when they started doing that as well. And the undertaking for that, the scale of storage that they need to work with, and kind of the reliability they have is insane. And then it also it does get back to the problem of syncing data. The core thing for Dropbox is a very difficult problem.
Yeah, but the fact that they were able to do it is like so impressive to me. I don't think I'll ever stop being a Dropbox customer, just because I didn't notice anything. I didn't notice any problems.
I know. That's like the true mark of good engineering, is that you don't even know what's happening.
Seriously. So what other kinds of applications are using Rust in production? And if there's some listener out there that's considering using Rust for some application, where do you think things are going in terms of adoption?
Yeah, it's looking great right now in the sense that, so we have a page on the website, rustlang.org/friends.html, which has a whole suite of companies that are now using Rust in production, and we're getting this steady trickle of companies that are adding their logos to that page as well. And it's kind of the common trend we're seeing among these is basically, it really is, we were a Python, Ruby, JavaScript shop or something like that, but we needed performance, but we couldn't go down to C++. So you have these high-level programmers who are intimidated by C++, and very rightly so. Like, even I am intimidated by C++. So kind of Rust is giving them this opportunity to basically turbocharge their application and kind of get it going as fast as possible, while also giving you the same safety guarantees you would expect from Ruby, JavaScript, and Python. And on the other end of the spectrum, we've seen a lot of companies that are working in C and C++, but they just want to make it. They have all these problems, these reliability problems, these segfaults, these security holes, and they want an escape hatch from that. And that's what Rust is serving their purpose as well. So kind of basically the exact use cases that Rust is targeting, we're seeing a lot of take up in production companies exactly around this kind of high performance, not worrying about C++, getting the performance I couldn't get before, those kinds of common trends.
We've spent much of this conversation talking about concurrency. What is in the works in terms of concurrency in Rust? What kinds of stuff are you working on?
Right now, I'm primarily focused on Tokio itself. So this is where we don't have the full stack is not quite realized just yet. It's kind of a work in progress where we have some base layers that are pretty solid, but we're trying to push through and kind of get all the way up to this Tokyo crate and kind of these composable services and all of this. So this is kind of fleshing out the various layers there, fixing bugs, taking feedback and tweaking the design as appropriate, and kind of making sure that's all pushing forward. But in terms of future avenues for concurrency in Rust, I think one of the coolest opportunities here is this library called Crossbeam. So this is a library in Rust which is giving you essentially a concurrency toolkit. So tons of various queues and concurrency primitives and synchronization primitives, kind of giving that all to you in kind of this nice toolbox to build extra algorithms on. And the coolest thing I think from this is that if you take a look at the space, at kind of the scene or landscape of concurrency algorithms, many of them are built for Java. This whole Java util concurrent package is incredibly high performance, highly tuned, very well respected, and very well written. And so the problem with that is all these algorithms are written with a GC in mind. So kind of assuming you have this garbage collector in the background. So it's been very difficult, and historically, for Rust to actually capitalize on this, to kind of get the same algorithms, kind of use these papers off the shelf to kind of use these cool data structures. But what Crossbeam actually did was it has a form of pseudo GC in a sense, where it's kind of giving you a lot of benefits of a garbage collector, where you kind of don't have to worry so much about when you deallocate data, which is especially important in a concurrent setting. But at the same time, it's not giving you this massive imposing runtime. So it's only this little tiny library is the only thing that matters, and kind of has this runtime behind it. So I've really wanted to kind of play a lot more with this than I have currently up to this point. But it's giving you the power of these GC, kind of what you would expect from Java, and kind of giving you the ability to take these algorithms and data structures off the shelf written for Java and just port them straight over to Rust. And they're actually faster than their Java equivalents, you'll find, because Rust's optimizations tear through a whole lot more, and you don't have the whole GC behind it as well.
So let's talk a bit about the open source community of Rust. How can people get involved, and what is the open source community like for Rust?
Yeah, this is one of the things that I've always been most proud of about Rust is that the community itself is an absolute pleasure to work with. So the community is very welcoming, very open, very helpful. It's a lot of fun to jump into, basically, for a small bug, for a big bug, for a documentation fix, like anything you want to do. It's a lot of fun to work with. And basically the best way to help out is kind of jump on IRC at irc.mozilla.org on the Rust channel. You could jump on the forums at users or internals.rustling.org. There's a subreddit, the rustling or reddit.com/rrust, and ends up you can have a little bit more higher quality than you'll see from other subreddits from time to time. But all of these forums have lots of people willing to help point you in various directions for ideas. Or just kind of, if you have various Rust questions, you can just ask them there and get them answered very, very quickly. So jumping into any of those places is kind of the best place to enter. And otherwise, you can check out Rust on GitHub at github.com/rust. And that has a whole suite of issues tagged on it. Some of them are tagged easy for kind of nice contributor bugs. Very detailed instructions for how to get up and running and get started. Various aspects like that.
Cool. Well, I think that's a great place to close off. Alex, thanks for coming on the show, and I really enjoyed talking about concurrency and Rust with you.
Awesome. Thanks so much for having me.
Thanks to Symfano for sponsoring Software Engineering Daily. Symfano is a custom engineering shop where senior engineers tackle big tech challenges while learning from each other. Check it out at symfano.com/sedaily. That's symphono.com/sedaily. Thanks again, Symfano.
Wow.